In the early 1950s, the world's first commercial jetliners started breaking apart mid-flight. Brand new de Havilland Comets, disintegrating at cruising altitude without warning. No engine failure, no pilot error, no explanation. The answer, when it finally came, traced back to a single geometric shape now built into every airplane window you've looked through. The reason those windows are round. That story begins with a mystery no one could solve. The de Havilland Comet represented the pinnacle of post-war aviation. As the world's first commercial jetliner, it promised to fly passengers higher, faster and smoother than the loud, vibrating propeller planes of the past. Airlines rushed to put these sleek, pressurized metal machines into service, and passengers welcomed a new way of traveling across continents. But the triumph did not last. Within a short span in the early 1950s, several brand new comets suffered sudden, catastrophic structural failures. These accidents did not happen during takeoff or landing, which were traditionally considered the most hazardous phases of flight. Instead, the passenger jets broke apart while cruising peacefully at high altitudes. At placeholder needs research. Feet, the pressurized cabins disintegrated without warning, leaving radar screens blank before pilots could transmit a single distress call. When the wreckage of placeholder needs research. Separate flights was recovered. Investigators found no evidence of engine trouble, weather damage, or pilot error. The metal fuselage had ruptured under pressure, costing. Placeholder needs research, lives and halting commercial jet travel. This crisis forced engineers to question the safety of high-altitude flight itself, launching a massive forensic investigation into a tiny, unnoticed detail in the cabin design. In the early 1950s, jet propulsion was supposed to represent the future of passenger flight, promising to shrink the globe by pushing civilian aircraft into the smooth, quiet air of the upper atmosphere. The Comet was the leader of this new era, designed to fly far above the turbulent altitudes of traditional propeller planes. When these advanced machines began breaking apart, the global aviation community faced a terrifying reality. The very concept of high-altitude jet travel was suddenly in doubt. The early phase of the inquiry produced only total confusion. The weather was clear, the winds were calm, and the flight crews were highly experienced. Because the disasters occurred in seconds, there were no radio distress calls and no witnesses to explain what went wrong. Investigators searched for familiar culprits. They analyzed the engines for failures, checked for fuel explosions, and examined the wings for aerodynamic flutter. Yet the recovered components showed no signs of these typical hazards. Every major system appeared to have worked perfectly until the moment of disintegration. This absence of an obvious cause created a severe crisis. Standard engineering practices had accounted for every known danger, yet some unrecognized variable was dismantling these airliners in mid-air, leaving investigators with a mystery that traditional rules could not solve. The task of solving this aviation mystery fell to Sir Arnold Hall, the director of the Royal Aircraft Establishment at Farnborough. Hall recognized that traditional laboratory tests on small, isolated metal samples could not replicate the immense forces acting on a complete, pressurized aircraft. His team needed to test an entire, full-scale airliner under simulated flight conditions, but doing so with compressed air was too dangerous. A sudden structural failure would cause an explosion, destroying the very evidence they sought. To solve this, the team built a giant steel tank capable of holding more than 200,000 gallons of water. They submerged a complete donor Comet fuselage inside the tank, filling both the inside of the cabin and the surrounding reservoir with water. By pumping water into the cabin, investigators could safely replicate the cabin to outside pressure differential of over 8 pounds per square inch without any risk of an explosion. They repeated this pressurization cycle, simulating takeoff, climb, cruise, and landing every few minutes. As the cycles climbed into the thousands, the continuous expansion and contraction began to take a toll. After approximately 3,000 simulated flights, a tiny fracture emerged at the corner of one of the square cabin windows. Under the rhythmic stress of the testing, this microscopic metal fatigue crack steadily propagated through the aluminum skin. Hall's methodical, water-submerged experiment successfully reproduced the exact structural failure that had occurred in the skies over the Mediterranean, pinpointing a highly localized vulnerability that had slipped past every design standard of the era. To understand why the metal failed, think of a passenger plane as a balloon. Every time a jet climbs to high altitudes, the air pressure inside the cabin must be kept high so passengers can breathe. But high above the clouds, the outside air is incredibly thin. This pressure imbalance forces the metal skin of the fuselage to stretch and balloon outward. When the aircraft descends and lands, the pressure is released and the fuselage contracts. This cycle of expansion and contraction repeats on every single flight. In a perfectly smooth cylinder, this pressure stress distributes evenly across the entire surface. However, cutting openings into the metal skin, like doors, vents, and windows, disrupts this natural flow of physical stress. On early jetliners, passenger windows were rectangular, featuring sharp 90-degree corners. As the metal skin stretched under pressure, the stress lines traveling through the aluminum could not flow smoothly around a sharp angle. Instead, they bunched up, concentrating immense physical force into a tiny, specific point at the very tip of each corner. This zone of high tension is known as a stress concentration point. Under the repeated loading of thousands of flights, this intense concentration of stress does something invisible to the naked eye. It begins to deform the metal on a microscopic scale. Eventually, a tiny crack nucleates at the corner. With every subsequent flight, as the cabin pressurizes and depressurizes, the crack grows a fraction of a millimeter. Over thousands of cycles, this microscopic damage silently creeps across the aluminum skin until the remaining structure is too weak to hold the pressure, resulting in a sudden, violent failure. By contrast, rounded or oval edges allow the stress lines to curve smoothly around the opening, spreading the load evenly. The realization that sharp-cornered windows could destroy an aircraft transformed the global aviation industry. This discovery did not stay confined to de Havilland. Regulators in the United Kingdom and the United States quickly updated their design mandates, forcing every commercial aircraft manufacturer to change how they built airplanes. Companies like Boeing and Douglas immediately abandoned square windows for future designs, replacing them with the rounded and oval shapes we see today. What looks like a simple cosmetic choice is actually a mandatory safety feature, codified in global aviation laws. From the Boeing 707 to modern Airbus jets, this structural shift became an industry standard. Every rounded pane on a modern flight represents a hard-won shield against the invisible forces of high-altitude travel. Modern passenger windows are engineered to be relatively small. Limiting the window size minimizes the amount of metal removed from the fuselage, restricting the physical stress that can build up around each opening. Within these small openings, the glass itself contains a highly functional detail. A close look reveals a tiny opening at the bottom of the middle pane, known as a breather hole. Modern passenger cabins use a 3-pane system. The heavy-duty outer pane bears the entire structural load of the pressurized cabin, while the middle and inner panes act as safety barriers. The breather hole allows air pressure to equalize between the cabin and the gap between the panes. This prevents moisture buildup, keeps the glass from fogging, and ensures the critical outer layer remains perfectly protected. Every rounded window is a silent reminder of a hard-won lesson. Today, these gentle curves protect millions of passengers daily, proving how modern aviation turned past tragedies into ultimate safety. Subscribe for more stories behind the everyday objects we take for granted.